In this question, we are once again looking at normal loading or axial loading along a bar. And the question is asking what is the value of the distributed force at a given location? So we need to figure out what this distributed force looks like for this problem, which contains a blade that is part of some type of windmill apparatus and is spinning with angular velocity omega. The omega is 105 radians per second, and it says that the length of a blade is 1 meter. And we also have an acceleration along this blade given by omega squared times quantity L minus x. This acceleration really should be written as a, it's a linear acceleration, and the angular acceleration would often be given by alpha. But at any rate, the question is about a distributed force. And we've already seen distributed force in the hanging bar question. And we can look at equilibrium here. And if we draw a slice with this blade, so let's say we're cutting right here, and this would be the right end, we would have the opportunity to draw an internal force P, okay, coming out of this slice. And it's going to be in equilibrium with the effects of a distributed force acting on the portion of the blade that we're analyzing. And we might say, like we've done here, that we're going to define x as going from the right end moving inward. Well, what does this distributed force look like? It looks like some type of density times acceleration times the cross-sectional area. And we can remember when we had the hanging bar that we had rho g a, where we had a density and gravity and a cross-sectional area. So the acceleration here is not g. In fact, it says that the problem says that we should ignore the effect of Earth's gravity, but it is going to be this omega squared times quantity L minus x. And what is, let's think about what this distributive force is really saying physically. It's saying that if you take a slice here, and we're saying that as you know we go along this in the x direction per some length, okay, or for some x if you like, as we're moving along the blade, we want to know what that force per that length is acting over that area. Okay, that's the distributive force. And that was going to be given by an acceleration that might be acting on that cross-sectional area, A, times its density. Another, well, okay, so this is the answer, but another way to look at the problem is to say, okay, what are the units involved? Well, we have a distributed force that has units of newtons per meter. We have our density. We have gravity, and we have cross-sectional area. And we have L too, okay? But I didn't write that in there. But those are kind of the quantities that you would expect to have. And so you can almost solve this problem just by trying to figure out what the units are telling us. If we had L, for example, then we would have an extra, let's say we were multiplying by L, which is what we kind of do, right? If we're trying to figure out, say, a force, not a distributed force, but a force acting on a mass, right? We do rho times the gravity times the volume. So if we did that, we would have kilogram meters per second squared, right? And that would be the same as newtons per meter. When we look at newtons per meter here, we can see that the newtons come out to be kilogram times meters per second squared, and then we are dividing by a length, then meters, okay? And so these two, the meters cancel out, and so these two quantities are going to have the same units. Well, let's go ahead and solve the problem. For this one, I think we'll just use Google. It doesn't seem to be too demanding. It's saying that we want to go at x equals L over 2. The length was 1 meter. and we have a cross-sectional area given by 3.3 centimeters squared, and we have density given as well. So for this, we'll go ahead and open up Google. You could do it in Python as well, but we did one of these other problems just using Python, so maybe this one we'll do using just Google. Okay, where can I put it? Yeah, it's pretty good. I think we can see this equation down here, and we can see the numbers up here. So rho is 1,000. Okay, and we have an omega squared. So we have 105 radians per second, and we're going to square that. Then we have our L minus X. So we're saying that it's at X over 2, or X equals L over 2. So we're at L over 2. So L was 1, so it's going to be 1/2 meter times the cross-sectional area, which is 3.3 centimeters squared, just like that. Okay, let's see what we get when we do it out. Okay, we get 1819 radians per kilogram per second squared. Now, this may sound a little strange. You're like, what does this deal with the radians? Well, in fact, we can ignore that quantity for this calculation. And so the correct answer is just going to be 1819 kilograms per second squared. Okay, or we can think of it as 1819 newtons per meter. All right, I hope you found this example useful. Thank you.